Hello guys, Sert here and welcome back to another video. Today I decided to explore what different types of empty products would look like. So the definition of the empty product we're going to be looking at, well, the multiple definitions, are anything times the empty product equals that other anything. Then the empty product to any power equals itself. And then the empty product to the zero would also equal itself along with anything else to the zeroth power. Now, of course, we can't just define this to be the default. So instead, what I'm going to do is for this video, I'll temporarily denote a number with a different product, with a different empty product, as the number with a subscript of the empty product. So x sub u to the 0 would equal u, which means u is just the empty product. So let's start with how these would work in multiplication. So for now, we'll focus on two different things with the same empty product. Like let's do 3 as our empty product, for example. 2 sub 3, so 2 with an empty product of 3 times, let's see, 5. No, I use 3 with an empty product of 3 just to see how this works. So 2 times 3 with the empty product of 1 is 6. But with this, since 3 with the empty product of 3 is here, remember this should act similar to 1. So you would get 2 times 3 over these empty products, which would turn into 3. And these 3's cancel out, just leaving 2, which satisfies this formula. Now, we also want to satisfy multiple other formulas, of which it's easy to prove that all of the other multiplication formulas are satisfied. And this is the definition. Well, this is the original definition of this, so we can just assume this to be true for now. So, next. What about, let's see. What about doing 2 with an empty product of 3 times 5 with an empty product of 3? Well, there's no 3 here, so we would just multiply these regularly, except we still have to divide by 3 because this is the empty product. So that's just 10/3 with an empty product of 3. 2 with an empty product of 3. So the empty products are supposed to stay as they are. So if you have two things with a 4 empty products, their product will also have an empty product of 4. And then there has to be a generalization for if you're multiplying things with 2 different empty products. So let's say you had 2 sub 3 and 5 sub 7. 2 times 5. 2 times 5. And then here, originally when we had 1 empty product, we would want to use just a 3 here. But we can't actually do that with this. So the method that I devised is using a square root. Now this does actually work with this system, because if you set the 7 to 3, you just get 3 times 3 square rooted, and that's just 3 back. So what this would turn into would be 10 over roots 21 with an empty product of roots 21. So there's that. So what about if you're doing this with different functions? Well, I just showed that an empty product to any power is just itself. But we can also show, let's say if we multiplied something like this, xu times xu, that's just x squared over u with an empty product of u. And then let's multiply that by x again, x squared times x, well, x squared over u times x. And then since these both have the same empty product, we want to do that. That's x cubed over u squared. And in fact, this same formula can be generalized for every power. And you'll eventually get x to the n with a u empty product equals u times x over u to the nth power with a u empty product. Actually, that should probably be written a little differently. There we go. I didn't show all of the steps here, but it is very easy to prove. In fact, I'll leave that as a homework assignment. So now that we found a general power rule, it is surprisingly easy to put this into a function like sine or the exponential function or even gamma function. Because using this, all you have to do, so f of an object with a different empty product, well, a general function, equals u times that function of x over u times, not times, using the u empty product. Which means it's also easy to find an inverse function. For that, you would just divide by u, take the inverse function, and then multiply by u again, which means that functions and inverses still stay functions and their inverses. Now the reason this works is because of a Taylor series. So if you have so let's say this function is a Taylor series from n, for n greater than or equals 0. You get x to the n, well, x to the n times c sub n, I don't know. Which means that you can just inject this formula right here, and you would get what I just showed you. So u x over u to the n times cn. And then you can move the u out, assuming this is a convergent sum that we're dealing with. And then you have x over u to the n, cn. And then finally, you just shorten that back down. Not an f, that is a u. F of x over u. There we go. And of course, you can't forget to do this. Now, don't worry, I did create a new notation for this. You don't have to write the weird parentheses with the u every time, because I know people already use that notation for things like the following factorial. So considering the other symbol is already used, that is x sub u, for many things, and especially with the parentheses, that can be used for following factorial, that can be used for pretty much anything. I decided to create a new notation for it, themed off of the notation for the modulus, and say that x imp u, emp. And again, that can just be read of x with an empty product of u. Now, of course, that might get a little odd to write. And I'm sorry, I can't really help you with that. But you can, of course, do x imp u, y imp v, like that. Okay, so, editor here. I forgot to add in a very specific thing that I want to do. And that is using the multinomials. So let me just show you the usual formula for this. And then there's another form called the multinomial form for multiple different objects. The actual formula here does slightly matter, but the numbers that we're using don't really. And here, all you need to know about how this multinomial is calculated is that it uses a bunch of factorials. I think it's like this, k1 factorial, k2 factorial, and so on. But the point is that we have all of these factorials, and every variable that we're entering is going to be 0. So, well, other than this r variable. So no matter what, n minus k, k, and all of that will just become 0. So, so if we substitute all the variables with 0, and this, the n is a 0, so 0 factorial equals 1, and all of these others are all 0 factorials, which means they all just equal 1. So in other words, the sum of things with different empty products to the 0. Actually, let me change this formula up a little bit to make it make more sense. X, U, K, like that. The sum of things with multiple different empty products is the product, well, to the 0, is the product of those empty products. XU to the 0, or in other words, you can just do UK, like that. So that makes for a very nice thing. So as an example, if you do 2 with an empty product of, well, I don't know, E, plus 5 with an empty product of 7 and 12 with an empty product of pi. I don't know, I'm just picking random numbers. Then you put these to the 0. You just get 7 times E times pi, which again is the product of all the empty products. So that's just a nice little proof. So now on to the outro. That's the basic idea of different empty products. And as for what I'm going to use this for, that is coming next episode. So, thank you for watching, thanks for joining, and I'll see you in the next one. Bye!